Alrighty, today I can identify the corresponding sides of similar figures to right proportions. I can use an algebraic rule to dilate a figure on the coordinate plane. I can compare the side lengths and angles of its shape and its dilation. I can explain how scale factor can affect the dimensions and area of a dilated figure. And when I say affect the dimensions, I mean perimeter and area, okay? All right, those are our learning goals for today. We are on number 7, okay? So we're going through dilations. And essentially, this card goes over what we gave you on a pink card, a reference card, all right? And this is everything you ever wanted to know about dilations but were afraid to ask, okay? So this right here is essentially here. So I suggest that you read it if you don't understand dilations yet, and a lot of you still are getting these wrong on assessments. Dilations create a smaller or larger figure. The shape remains the same, so are the angles going to remain the same? I hope you said yes. But the size does not, because remember the small square and the large square, just because you increase size on a shape, the angle measures are what maintains it, okay? SF, it refers to scale factor for all purposes that I am doing this. I always write SF, not scale factor. Dilations always involve multiplication, okay? Always. Okay, so you're going to have a scale. It's the only transformation that does not maintain congruency. Why? I hope you said because it changes its size. Okay, when you multiply by something, it changes its size. Remember, we have A and we have A prime. A prime is the new. So A is the original, A prime is the new. Multiply by a scale factor less than 1, and the new image is smaller. Multiply by a scale factor greater than 1, and the new image is larger. Okay? What about if you multiply by 1? What happens? You're right, it stays the same. Okay? Be careful. Here's an example. 7/4. It looks like a fraction, doesn't it? But are fractions, just because they're fractions, do they mean they're smaller? No, because here your numerator is greater than your denominator. So 7 divided by 4, if you put it in your calculator, 7 divided by 4, you find out it's 1.75. So that means if you had a scale factor of 7/4, you're actually going to have a larger image, okay? Whereas 2/7, because the numerator is smaller than the denominator, you actually are going to have a new figure. And this is 8,571, blah, 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 blah. So I'm just going to round it to 0.29 for today, okay? So actually you're going to have an image, a new image that's smaller. If you need to find the scale factor, just say no. See right here, no? No. Use new over old. You can use an X or a Y or the corresponding side lengths. You can use any of those things, and you put your new measurement over your old measurement, and then that will tell you, simplify that, and it will tell you what the scale factor is, okay? Dilation rules always look like this. It means you have a scale factor times your X and a scale factor times your Y. And a lot of times they say it's multiplied by a scale factor of, what about if they use the word K? Okay? So then it would be KX times KY. It's abstract. It's a different way of asking the same question. We don't know what K is, but it is the scale factor. Okay? Let's flip the page. This goes into it in a little bit more detail, so if you are struggling with this, please pull this out and read it. It tells you exactly how to find the scale factor using corresponding points. It shows you the new x over the old x, or the new y over the old y, or using corresponding side lengths, the new over the old. So this is a little more detailed. I'm kind of doing things rather quickly on these notes, okay? Dimensional change. I don't know why we struggle so much about this. If they're talking about perimeter, it's you multiply the old perimeter times the scale factor to the power of 1, because it's just in the first dimension. So you just take the old perimeter and multiply it times the scale factor of 1. If they are talking about area, you take the old area, or when I say old, I mean original, okay, times the scale factor squared. And a lot of you will do things that don't make any sense, like you don't realize that something squared doesn't mean it's doubled, okay? So in other words, 6.6 squared is not 12.12, okay? Let's just use 6.5 because that's easy. 6.5 times 2 is 13, but 6.5 squared is 42.25. So if I had an original area and I had a scale factor of 6.5 squared, it means that my new area would be 42.25 times larger, okay? So just trying to clear that mess up. So here's here is a cube is dilated by a scale factor of 3/4 to create a new cube. Okay? The surface area of the new cube is, oh, I don't like this problem. We should have changed this problem. Let's do a square. I want you to clean those out. Is dilated by, because a square, okay, well, I guess it doesn't matter, a cube. All right, so the surface area of the new cube, because see, you wouldn't do surface area. Well, surface area, it wouldn't ask this. Surface area is actually perimeter. But because it's a cube, they want you to take into effect that it's three-dimensional, so you have more, so let's do a square. Okay, let's go back to here and write a square is dilated by a scale of 3/4 to create a new square. Okay, says the square, the see, I'm messing up the whole thing. This is a really bad situation here. Let's do one in your packet, okay? I'm going to come back to this and do one in your packet, all right? So let's go down here. This is similar figures and proportions, what proportion could be true to prove that they are similar figures. So this is where we say 1, 2. We have figure 1 and we have figure 2. And I am going to do this. I'm going to put a plus sign here. If I flip this, this side is actually up here. So this is going to be here, a plus sign. I'm going to put an open sign here, an open sign here. I am going to do a squiggly line here and a squiggly line here. And then I'm going to do a straight line here and a straight line here. And then I'll do a, a dot here and a dot here. So here we go. So if this is A, I got to prove to see which one's true. So A. I've got O, which is OP right here. So this is on figure 2, and it's a plus. Then I have HD, which is figure 1, and it's a squiggly line. Then they say MN is figure 2 and a straight line, okay? And then DE is 1 and a straight line, but the problem is right here, so it can't be A. Let's go to B. I've got MN. M and N is 2 and a straight line. Then I've got DE, which is 1 and a straight line. And then I've got GH is 1 and an open circle. And PQ is 2 and an open circle. So those are comparing, but I've got 2, 1, 1, 2. I really don't like that. The 2's need to be on top, and the 1's on the bottom, or 2, 2, or 2. It just isn't going to work. Let's try C. NO. NO is right here, and it's 2 in a closed circle. And then I've got EF, which is 1 in a closed circle. That looks promising. PQ. PQ is on 2, and it's 2 in an open circle. And GH is 1 in an open circle. There's my answer, C. Okay? So that's how I would do those. And then let's look at a couple of